Hello, I'm Carlos Lemin, a postdoc researcher with Jens Cover in the Cognitive Robotics Department at the Delft University of Technology. And it is a pleasure to talk about our research in interactive imitation learning for robots learning from non-expert users in this RSS2020 workshop on closing the academia to real-world gap in service robotics. What is a service robot? So for the International Organization for Standardization, a service robot is the one that performs useful tasks for humans or equipment excluding industrial automation applications. And the International Federation of Robotics adds to this category systems based on some degree of human-robot interaction. So service robots could be ranging from robots that are executing tasks for humans completely autonomously, or executing the task in a team also with collaborating with a human user, or also helping users that have some physical limitations. In Industry 4.0, both industrial and service robots are required to be more adaptable and flexible, and this means that they should be easily programmable, even by non-expert users. And with non-expert users here, I mean people that don't have the technical background for programming a robot. So one of the possibilities for achieving this is using machine learning for programming behaviors for robots. Imitation learning is an approach in which a human expert is teaching the robot how to execute a task, giving some demonstrations of this execution of the task. But most of the approaches in imitation learning have the limitation that they work with the assumption that there is always an expert human demonstrator for reproducing the task and giving the right data for obtaining a policy. And also they don't consider much that the humans could be executing some mistakes during the demonstrations, or that the data that is being demonstrated could be inconsistent sometimes. So with interactive imitation learning, we cover the set of approaches in which the human teacher is part of the learning loop. So the human teacher is observing the agent environment interaction and could every time provide some signals of feedback in order to improve the agent performance. And the signals could be classified in different kinds that will be either evaluative or in the action domain. Basically, in the first case, it could be reinforcements, which are signals, positive or negative signals that the user will give about the execution of the actions, or preferences or rankings, in which the user will compare different executions of the policy. In the domain of the actions, the user could give partial, either corrective demonstrations or relative corrections about the action that was executed at certain specific time steps. In this last one, relative corrections is a domain in which our research is focused. So we have both a framework called COACH, Corrective Advice Communicated by Humans, in which the user is observing the actions that the agent is executing, and occasionally the user could give coarse corrections, which represent the direction wherein the action should be modified. For instance, it's increasing or decreasing the action. So this works with the assumption that the user is not an expert, so he or she doesn't know what is the optimal action or the right magnitude of the optimal action, but just the trend on how this action could be modified in order to improve a policy. So basically here it is a high-level pseudocode of the algorithm in which while the agent is trying to execute the policy, the user is able to provide some feedback. So every time step, the agent observes the world with the state, the current policy is computed for obtaining an action which is executed, and then whenever the user considers this action could be modified, the user will give some feedback to the policy to the agent in order to increase or decrease the action. And when this happens, it is computed an error signal based on the correction given by the user, increase or decrease, multiplied by the constant error. This under the assumption that the user doesn't know exactly what is the error or the right action to execute. So we have to work with a term at the beginning that is initialized according to the domain of the task. And then the policy is updated immediately. So next time that we have a new policy updated by the feedback given by the human. So for instance, in this video of the carpool, we could see the user first trying to teleoperate this carpool with these coarse commands of like increase apply force to the right or to the left, but it was not successful. While the same interface was used for providing this same kind of coarse feedback, it was possible to train a policy giving feedback like increase or decrease the action, like move more to the right or to the left. And then within few iterations, it was possible to shape the policy that was able to keep the balance of this ball. So actually it was interesting because in several experiments, we have observed that users that are not able to demonstrate a task were actually able to teach the agent how to perform it. You could see here in this another example, the policy resulting from user training this system with also this corrective feedback, in which the user was advising how to increase or decrease the voltage that was controlling the position of this car on this inverted wedge. And then without even understanding the domain of the voltage that will move the car in the right direction, the user was still able to achieve this policy that was keeping the balance of the system. We could see here a different application in the context of RoboCab. With the now robots, we were able to train a system that was controlling the dribbling engine system for this team in my previous lab. Basically, the user had to correct the velocity request for the walking engine in order to make the robot to walk against the ball in order to push it to the desired direction while also avoiding the opponents. So basically the system was about walking and pushing the ball without actually executing a specific kick, but just pushing by accident the ball. So the user was giving feedback like increase the velocity in the X or Y axis, or the increasing or decreasing the rotational velocity, and so on. Another example here was for these movement primitives trying to write down symbols. So at the beginning, this M character was obtained from some demonstrations, and then later on, the users had to advise how to modify this trajectory in order to improve the shape of this M letter. So basically, the user was giving feedback about move more to the right or move upwards or so on. And then within few iterations, without the need to specify which exact position the robot should be at every specific time step, it was possible to shape a trajectory that was having a nice shape or a better shape according to the human teacher, as it is possible to see in this execution. So basically it took only 5 episodes with coarse feedback, and this was the result. We also have extended this concept of corrective feedback in order to learn policies in end-to-end approaches. Basically, we here combine this concept also with state representation learning. So we have a network structure in which we have 2 different cost functions, one for reconstructing the observation, which is a raw image, and the other one that is the actual output of the policy, which is shaped by the corrections given by the human teacher. So for instance, we could see here a car racing task. In the right, we could see the output of the autoencoder, which at the beginning is very, very, very bad, while the user is providing some corrections to the agent. Basically, at the beginning, the experience for the user is similar to trying to teleoperate the agent, because the user is giving feedback all the time, like increase the velocity or move to the right or brake or so on. But after 50 episodes of training, it is possible to already obtain a high performance policy, which is in the same level of the best results obtained with reinforcement learning, but being hundreds of times faster than the reinforcement learning agents. We could see here also another application for this, also driving a small car, in which it has a camera on board and it has to drive the right lane of the circuit. So the user is providing feedback with this computer that it has in his hands. So after some laps, it is possible to obtain already a good performance. But we could see at the beginning how is the performance of the output of the autoencoder. At the beginning is very bad, but when it is getting more and more data, it is possible to have a better representation of the observations. And then later, it is possible to, within a few minutes, it is possible to obtain a policy that is successful in the task. We could see that the user is not providing any commands for correcting the policy anymore. We also tested this with this pusher task. So in the left, we could see the output of the autoencoder at the beginning, but then it is getting better after the robot or the system is getting more and more data. So basically, the task is about pushing this object out of this box from the bottom side. So at the beginning, also, the user has to give feedback all the time. So the experience for the user is similar to being teleoperating the agent, but with more and more training time, the need of feedback is reduced, and then within 20 minutes, it is possible to obtain a successful policy. So we also have extended this concept for learning policies end-to-end in the context of environments that don't have a Markovian observation. So we also, for this, we also leverage on state representation learning. In this case, we use the observation prediction cost function. Basically, the agent is learning the policy, but at the same time, it is learning a world model of the environment. So learning this world model of the environment is helping to obtain some temporal features that explain the state of the environment that is not explained by the observation itself. So for instance, here, we have these two tasks, the mountain car and the pendulum swing up. So the observation is the environment that is in here in the right. So this environment only, or these images only show the information about position, but not velocities. So it's important to learn temporal features about this task or about this observation. So we here in the left observe the input to the network, and then here in the middle, the observation prediction given by the world model that is being trained simultaneously while the user is giving feedback to the policy. So at the beginning, we could see that the performance is not so good for predicting the next observation in the next time step. But then within few episodes, it is possible to improve the performance of the observation prediction, but also the policy. So for the case of the mountain car, it is possible after a couple of minutes to learn a good policy. And for the case of the swing up pendulum, it was possible after only 12 minutes. We also validated the system with a real swing up pendulum. So in this slide, we could see in the left, the input to the network, which is the camera image that is placed in front of the swing up pendulum. And then in the right, we could see the prediction of the next time step observation. So after 12 minutes, it was possible to obtain a successful policy. So it keeps the balance until we occlude the camera image. We also validated this approach in this task about selecting oranges. So we have these oranges in this conveyor belt, and there is a camera on top, which is observing the environment, and this robot should go to intercept the position of the oranges when they are in front of the robot. But the problem here is that the camera is only observing this wide area of the conveyor belt, which means that the robot has to make decisions based on information from the past. So that's why it is important here to learn the temporal features that explain environment state. So the user was giving feedback to the robot, and then in less than an hour, actually in 45 minutes, it was possible to learn to successfully intercept the position of the oranges in most of the cases. And then we extended this task to a more complex scenario in which the robot didn't have to only to intercept the oranges, but also to reject pairs when they were in the conveyor belt. So the robot had to move away when there was a pair in front of the robot. So for this, we extended the training with 15 minutes more. Basically, the user had to be given feedback for making the robot move away when there was a pair in front of it. And for this, a non-expert user was given feedback, and it was possible to learn in 1 hour this complex task, learning from scratch temporal features only based on having the input of the human relative occasional corrections. We have also combined this with reinforcement learning. So basically, this corrective feedback coming from the human teacher is taken by a reinforcement learning agent as a perturbation or a noise exploration. So based on the return that the reinforcement learning agent could compute, this feedback given by the human could be taken for updating the policy, or if the return associated to this feedback is negative, basically the occasions in which the user is providing wrong or mistaken corrections, the reinforcement learning agent is aware of this and could filter out these executions and not update the policy in this direction. So with this combination of approaches, we could have the benefit of both worlds, basically speeding up the learning process with the insights of the human, but at the same time using the return computation for filtering out the mistakes that the user could be giving with its corrections. We have validated this approach in different scenarios. For instance, here, the ball in a cap game. This task, the robot has to move the swinging ball in order to make it fall inside this cap. So we could see here in this video, the policy resulting from the first episode of having human feedback. So basically, the user just told the robot to move more to the right and to the left. So this behavior of swinging the ball was already obtained. But then incrementally, with more episodes, this trajectory was improved with more corrective feedback. Basically, the user in front of the robot was telling the robot to move more to the right or backwards or so on. And then within 23 episodes, it was possible to obtain a policy that was successfully achieving this task. So we can see here the final policy. And these results were actually 4 times faster than the results obtained with a state-of-the-art policy search algorithm. So we could see that the benefit of having the human in the loop was quite a lot. More recently, we have extended this approach for learning with corrective feedback to a scenario in which the user could give feedback not only in the action space, but also in the observation or state space. So this is necessary because for some tasks, the actions are not so intuitive for the user. This could happen, for instance, in problems where the actions are defined in a high-dimensional space. For instance, a legged robot. For this kind of tasks, it's hard for the user to give feedback in all the actions, but the user could give feedback about the pose of the robot in general, for instance, the orientation of the body. And then with this feedback, we should be able to translate this into what are the right actions to obtain this correction or relative correction in the pose or orientation of the body of the robot. So for this, it is necessary to learn simultaneously an inverse dynamics model. So while the teacher is providing feedback to the agent is also learning an inverse dynamics model that is helping to translate this state space feedback into the actions that are obtaining these transitions suggested by the teacher. We have validated this in some simulation scenarios, but also with a couple of tasks in this real KUKA robot arm. So this fishing task is about this ball hanging from the end effector of the robot, which is swinging, and the robot has to place it in this cap. So the user is giving feedback in the end effector's position, and the robot is actually learning what are the velocities in the joint space necessary for placing this ball in this cap. Then it is possible, as we see here, after 20 minutes of training, we obtain a policy achieving this task. A similar task here was about writing symbols in this whiteboard with a laser pointer. So the user is providing feedback in the Cartesian space in the image that is segmenting the position of the laser. And then after 6 minutes, it's possible to have these policies that are writing down these symbols. For instance, here, we write down core, the acronym of our department. After the validation of all these approaches, we have observed that in our experiments, the users, for many tasks, they were not able to demonstrate or to operate these tasks, but still they were able to give feedback and achieve policies that were successful. So these learners outperformed the capabilities of the teachers. We also observed that for the case of end-to-end policy learning, it was possible to have more data-efficient agents when we were combining this corrective feedback with state representation learning techniques. Also, we observed that when we use the human teacher inside a reinforcement learning process, we obtain the advantages of the two of these worlds. So basically, we can speed up the reinforcement learning process with the insights of the human, but also the interactive imitation learning is improved based on the return that the reinforcement learning agent could compute. So for instance, when the tasks are also about reducing or optimizing terms that are not so evident for the user, the reinforcement learning can take over of that. For instance, when we need to reduce the energy consumption, this is not so evident for the human teacher to understand how to reduce this, but the computation of a reward function and using this return for the policy is also helping the learning process of these policies. Or also when there are tasks that require precision that is beyond the capabilities of our perception, then the optimization of the reinforcement learning agent could be also leveraging the use of external perception or sensors that are being used for computing the return. And this could help to keep optimizing a policy after the user reaches a certain level of good performance. Also, we observed that the effort of a user could be reduced if we focus only on giving feedback in a specific condition for the environment. And then with these corrections that the user gives for training a policy in this particular case of the environment, we learn an objective function. And with these objective functions, we could use reinforcement learning for training autonomously a policy in the other conditions or in different scenarios for this environment. Then it is not necessary anymore the intervention of the user inside the learning loop. And this is important because we human users get tired, we get stressed, we lose our focus after a certain time. And this is an important key to have in consideration when we are dealing with robots that interact with humans. So in general, this approach for learning from human correction is getting closer to the possibility of non-expert users to program or adapt these robots that are going to be more and more in our environments, like household environments, for instance. So it is feasible to keep developing methods that one day will be making life easier for the users without requiring to be expert roboticists. So with this, my presentation is finished, and thanks very much for your attention. But also, I have to mention that all this research is possible thanks to the collaboration of all these great researchers. So thanks very much, and looking forward for the discussions during the workshop in RSS.